Hello everyone, welcome to the live interactive session for the second week of the course Structural Geology offered by NPTEL. My name is Rajiv Mukherjee and I am Prime Minister's Research Fellow at the Experimental Rock Deformation Laboratory of IIT Kanpur, and I am currently hosting these live sessions. And for today's live session, the topic of discussion will be on measurement of structural attributes, which is the content of the course for week 2. So this is the outline of the course Structural Geology. So we already covered the first week's content, which was basic concepts of structural geology, what structural geology aligns to, what are the main areas of inspection that we go for in structural geology, what are the key elements, and some simple multiple choice questions that were solved the last week. And so this week we are mostly discussing about structural elements, measurements, and stereographic projections. That is the content of week 2. For the coming week, we also have the topics like concept of strain, concept of stress, rheology of materials and rocks, deformation mechanisms of materials and rocks, then foliation and lineation, then talking about ductile deformation, mechanisms of folding and superposition, and then ductile deformation, which includes boudinage and related structures, and then of course brittle deformation, which includes fractures, joints, and faults. And then comes along the concept of ductile shear zone and the concept of lithostructural mapping and the conclusion of the course. So the live interactive session is being hosted weekly, mainly to address several doubts that are the people are having during the course, and also to actually involve in problem solving interactions. And the duration of these live interactive sessions will go on for 12 weeks, simultaneous to the course itself. And this is the second live session. Today is 1st August 2026, and each Saturday from 5 p.m. to 7 p.m. I will be hosting these live interactive sessions. So let's get on to today's discussion session. So about today's live interactive session, so if we summarize what we have already learned in week 2, that will be definition of structural attributes such as strike, dip, pitch, plunge, rake, etc. That means pitch, and their geometric relation and measurement techniques, description of equipments and their uses such as the Brunton compass, the clinometer compass, and other tools that we generally use for measuring the attributes in the field. Fundamentals of geometric projections, like understanding the stereographic projection, upper hemisphere, lower hemisphere projections, and then equal area net, equal angle net, and how these things are being used for interpreting different kinds of structural geometries that we generally see in the field, and also interpretation of structural data from stereo net problems, right? So today's topic of discussion will mostly be evolving around deriving trigonometric relations between structural attributes through different multiple choice questions, solving conceptual questions related to the structural attributes and stereographic projections, and then summary and conclusion. And if time permits, we may also plan for the upcoming live sessions depending on the query of the people who are joining these live sessions. Okay, so let us move on to the question answer solving session, because I have planned near near about 20 multiple choice questions. Most of them, I mean, in fact, all of them are likely be numerical problems, since solving questions regarding the structural attributes are mostly numerical heavy. So I have designed several these conceptual problems that require trigonometric calculations and 3D diagram or 3D conceptualization of different structures, so that we can also solve some conceptual problems related to stereographic projection of different kind of structures. Okay, so the first question says, a mineral lineation lies on a foliation plane of attitude 120 slash 50 degrees southwest. The trend of the lineation measured from strike is 35 degrees. The plunge of the lineation is therefore closest to option A 18 degree, option B 28 degrees, option C 35 degrees, and option D 42 degrees. So if I repeat the question again, so the question says that we have been given a lineation that is being contained on a foliation plane. Now the attitude of the foliation plane is such that 120 slash 50 degrees southwards means the strike line of the foliation plane has a bearing of 120 degrees, and 50 degrees southwest is the amount of dip, and the trend of the lineation measured from the strike is 35 degrees. That means from 120 degrees, if we move 35 degrees, then it will give us the trend. Of course, these rotation from the strike line itself has to be clockwise, means it should follow the right hand rule and not the other way, or the clock and counterclockwise manner. So rotating clockwise from 120 degrees, 35-degree due, so it will be placing the direction of the lineation, the trend of the lineation will be towards 155, right? So this is the information that is being given. So I will pause for several minutes. I will let you think. If you have an answer, if anybody has joined this live session, so if anybody has any answer, they can say the answer, or else I will provide some time to think about the solution to this problem. Then I will go step by step how this problem is to be dealt with, and we will then eventually calculate the correct answer. Okay, so let us try solving this question. So strike is, sorry, 120 degrees, right? Deep is 50 degrees. So let us consider strike as phi. Let us consider deep as delta, and we have also been given an information is that the trend of the lineation is 35 degrees from the strike. So we consider trend as, say, theta, right? Then what will be the value of trend? 120 degrees plus 35 degrees, that means 155 degrees. So this is theta. Now we introduce a term, structural bearing. This essentially defines the difference between trend of line and the strike of a plane. So in this case, structural bearing is essentially theta minus phi. Let us consider this angle as delta, this delta, and which is essentially 35 degrees that was actually given. Now we will use a trigonometric relation, that is, you can note down this formula: tan of p, small p, is equal to tan of delta times sine of this triangular delta. Now this p will be the plunge of the lineation. So then by putting the numerical values, we will then calculate these as tan of 50 degree times sine of 35 degrees. Right? What will be the value if we calculate using a calculator? So I am using a mobile phone. So tan of 50 degrees is 1.1917 times sine of 35 degrees, which is 0.5736, and this product is 0.6836. So then for calculating the plunge, all we need to do is to take the inverse of this value. So we need to calculate the arc tangent of this value. So this is 0.6836, and this is equal to 34.35 degrees. So which is close to, we can say, 35 degrees. That means option C is the correct answer, and we can write the line plunges 35 degrees towards 155. So this is the azimuth or the trend. We can say the line is plunging 35 degrees towards 155. So this was the first question. Now we move on to the next question. So the next question says, a lineation has a trend of 165 degree and plunge of 30 degree on a bedding plane, striking 135 degrees and dipping 45 degrees southeast. So the pitch of the lineation east closest to option A 24 degrees, option B 35 degrees, option C 42 degree, and option D 66 degrees, right? So in this case, what we have to do, if we just look into the question, so again a lineation is being given and the trend of the lineation is clearly mentioned, that is 165 degrees. The plunge of the lineation is also given. Bedding plane strike line is also given, it is 135 degrees, and the deep information is also given. Then using all this information, we have to calculate what will be the closest pitch angle measured from the strike, which is at having an azimuth of 135 degrees. So again, for this problem, I will let you think for a couple of minutes. It is also an interesting trigonometric problem to address, and we will use another trigonometric relation. But I first encourage you to try yourself to actually find out what is the probable trigonometric relation that you can use to address this question. And then, of course, we will discuss after a couple of minutes how to actually tackle and solve this kind of trigonometric relations. Okay, so let us solve this question again. So we can also write down the information that we are given. So the trend of the lineation, which is, we can say, is theta, is 165 degrees. The plunge of the lineation, which is small p, and it is 30 degrees. The strike of the bedding plane, which is phi, and it is 135 degrees. And the deep of the bedding plane, which is delta, and which is also 45 degrees towards southeast, right? Okay, so now we can of course calculate what is the structural bearing. And that is of course the difference between trend and strike, right? Therefore delta will be 165 degrees minus 135 degrees is equal to 30 degrees, right? Now we can use another important trigonometric relation. So you may write it down. Cosine of the pitch or rake is equal to cosine of the plunge times cosine of the structural bearing. So this is the formula. Cos r is equal to cos p times cos delta. So we can obviously calculate what is cos of 30 degrees times also the cos of 30 degrees, right? So the value is 0.75. Now if we take the inverse of this 0.75, we will get the pitch or the rake of the lineation. So rake is equal to inverse cosine 0.75. So we have to calculate the arc cos in the arc cosine of this angle. and the angle is, the value of this inverse function is 41.4 degrees, which means is close to 42 degrees. So again, option C is the correct answer, and we can write that the pitch of the lineation is 42 degrees. Okay, so this was the second problem, and also we learned about two different trigonometric approaches to evaluate what is the what is the trend, pitch, plunge, and dip of a lineation lying on a plane with certain attitude. Okay, so we will move on to the next question. A bed dips 55 degrees due east. The apparent dip measured along an azimuth of 060 is approximately 35 degrees, 38 degrees, 48 degrees, and 55 degrees. So this is a simple problem of measurement of apparent dip along a certain direction other than the strike or the dip direction, right? So the problem is asking about the apparent dip of a linear of a bed which has an attitude of 55 degrees, the dip amount, and the dip direction is east, and the question asks to measure the apparent dip along 060. So we have already discussed the formula in the past two questions. So I think I will pause for a minute or two and let you think which of the formula that we have studied already can be applied in this scenario to actually calculate what is the apparent dip along the certain direction given. Okay, so let us now dive into the problem. So the key word here is that you have to calculate the apparent dip. Now, apparent dip along a certain direction is equivalent to the plunge of a line along that certain direction that is being laid on the plane. So I can write this down, and you should remember this in this way. It's like apparent dip along a certain direction is equivalent to the plunge of a line along the same direction, along that same direction, a line that is virtually contained on that plane, right? So we just need to determine the plunge. In this case, plunge along 060, right? So we have to calculate P. Now what information do we already have? We have the deep amount, which is delta, and that is equal to 55 degrees. We have the dip direction, right? Dip direction is, the dip direction is towards east, right? That means 090. So what will be the strike? Right? Because deep direction and strike are perpendicular to each other. Therefore, using this information, we can calculate the structural bearing, that is 60 minus 0 is equal to 0. Right? Sorry, 60 degrees. So we can use this value eventually to calculate what will be the plunge amount. So the tan 50 degrees 1.1917, and sine 60 degrees is equal to 0.866. So if we multiply these together, so we are having 1.032. And then eventually if you take the inverse, so 1 point inverse of or arc tangent of 1.032 is equal to 46 degrees. So the approximate answer will be option C, because this is the closest, right? So 46 degree is the actual plunge amount, but the approximate value is close to 48 degrees, and therefore option C will be the correct answer. So this will be the apparent dip. The plunge amount and the apparent dip are nearly the same, or I mean physically the same in this case, and we have calculated the value, which is 46 degree, and it is pretty close to the what are the options are given is like 48 degrees, right? Okay, so this is how we also apply the same formula to a different approach. And then now move on to the next question, which is question number 4. Okay, so the question says successive structure contours of a bedding plane differs by 50 meters in elevation and are separated by 120 meters horizontally. The true dip is 18 degrees, 23 degrees, 31 degrees, and 41 degrees. So now we actually need to calculate the dip value from the information given about the elevation and the horizontal separation, which is 120 meters. So it is a pretty basic trigonometry calculation, and I will pause for a minute and then we will eventually solve this problem. But I think that it is very uh, it's a very basic question. It's like basic trigonometry, and I guess everyone should get this easily. I hope that people understand the question easily. Okay, so the question is pretty easy because we have different contours. So what we are saying is that the horizontal difference from this point till this point is 120 meters, and for that we need, I mean, we are crossing over a vertical distance of 50 meters. So If we have a vertical line like this and we have a horizontal line, so this will be the true dip of the contour. I mean, true dip of the bedding plane. So the true dip can be calculated as, no, just let us write dip as delta, because that's we have been maintaining since the first question. So 10 of delta, and we can write as 50 over 120. So this is 0.4166, and therefore the delta will be inverse of 0.4166. And the value is actually 22.62 degrees, which is close to, or actually approximately equal to 23 degrees. So option B is the correct answer, as we can write that the true dip of the bedding plane is 23 degrees. Okay, so let us move on to the next question. And this says is that there's a sandstone bed is 25 meters thick and dips 40 degrees. The outcrop width measured perpendicular to the strike is option A 19.2 meters, option B 32.7 meters, option C 38.9 meters, and option D 48.5 meters. This is also very simple compared to the last question. It is just basic trigonometric operations, and eventually we can also calculate. So again, I will pause for a minute and then we will eventually solve this problem, and we will see that how this problem is being tackled. Okay, so if we just draw the diagram here, so this is the bed, and the true thickness is say 25 meters. So then we have to calculate the outcrop width, that is this one. Say for example this angle is theta, this is theta, and this line eventually is parallel to this one. So we consider this as A, B, and C. Say this is a triangle, the right angle triangle ABC. Now AC is equal to 25 meters. Angle ABC is equal to deep amount, so which is basically 40 degrees, right? Okay, so now let us change this angle to delta. Then what we have to measure is AB. Calculate the outcrop width AB. Right? So what we can write is that AC by AB is equal to sine theta or sine delta. Therefore, AB will be AC by sine delta, and that will be exactly 25 divided by sine of 40 degrees. So if we calculate what is sine 40 degrees, so this is basically 25 divided by 0.643. And that is equal to 38.9 meters. So the correct answer is option C. That means the thickness of the or the width of the outcrop of the bedding plane is 38.9 meter. Okay, so this was question number 5. So let us now move on to question number 6. So the question asks that a bed dips 35 degrees. At what horizontal distance from the upper contact should a vertical drill hole be placed to intersect the top of the bed at 150 meters of depth? Right? So if we have a surface and this is the bedding plane and the deep delta is 35 degrees. So the question is being asked, so from which distance, say for example this distance, this is AB, let's consider. So from here, if a drill hole is being, I mean, a hole is being drilled, so eventually this depth has to be 150 meters. So the problem is simple in a sense because you have to calculate. So if this depth is say C, so the depth has to be calculated as, sorry, AC is 150 meters. The deep amount, the depth of the bedding plane is 35 degrees. Now we have to calculate the distance AB. So what we can write, AC by AB is equal to tan 35 degrees. Therefore, AB is equal to AC by tan 35 degrees, and the value will be 150 divided by 0.7. So which is essentially 214.2 meters. So the correct answer is option C. The horizontal distance is 214 meters. Okay, so move on to the next question. A horizontal sedimentary layer is folded into a cylindrical fold with a fold axis plunging 30 degrees towards 090. The plunge of the hinge line measured in the field will be 0 degrees, 30 degrees, 60 degrees, or 90 degrees. So the information that is being given is that a horizontal sedimentary layer is folded into a cylindrical fold with the fold axis plunging 30 degrees towards 090. The plunge of the hinge line measured in the field will be this four given option. So the approach is that since the fold is essentially cylindrical, therefore the fold axis and the hinge line will have the same plunge. Therefore, for a fold, cylindrical fold with fold axis plunging 30 degrees towards 090, the hinge line will also plunge 30 degrees towards 090. Therefore, the plunge of the hinge line measured in the field will be 30 degrees. So option B is the correct answer. Okay, so move on to the next question, question number 8. A limestone bed shows an apparent thickness of 18 meters in a vertical quarry face perpendicular to strike. If the bed dips 40 degrees, then the true thickness is 11.6 meters, 13.8 meters, 18 meters, and 23.5 meters. So we already solved a problem similar to this one, and I think that I can provide a couple of minutes to think about this problem, and then eventually we will solve the similar kind of problem we already dealt with. Okay. Okay, so this kind of problem we should can solve it by just simply having a diagram. So if this is the surface and this is the dip of the bed, and this thickness is given as the true thickness. So this is A, B, and C. So given that the apparent thickness, now the apparent thickness is AB, is 18 meters, right? Measure perpendicular to the strike. Now therefore we have to calculate the, so now the deep amount of this bed is 40 degrees. Therefore we have to calculate the true thickness, which is AC, right? So what we have been given, angle ABC, which is delta, which is 40 degrees, right? So AC by AB is equal to sine of 40 degrees. Therefore AC is equal to AB times sine 45 degrees. Sorry, sine 40 degrees. So the AB is 18 meters, 18 times sine 40. So sine 40 is 0.6427. So 18 times 0.6427 is 11.56 meters, or 11.6 meters. So option A is correct. That means the true thickness, of the bed is 11.6 meters. Okay, so this was question number 8. Now let us move on to question number 9. A fault plane dips 60 degrees and carries pure deep slip displacement. The rake of the slicken side lineation is 0 degrees, 30 degrees, 60 degrees, and 90 degrees. Okay. So for a pure deep sleep fault, there will be no strike slip component. Hello? Okay, I can consider. Uh, yeah, that is correct. So apparently, this thickness is, so if this is a vertical section, I guess, and if this is the bed, and if this is truly vertical and perpendicular to the strike, yes, if this is actually perpendicular to the strike and the face is itself vertical, then the apparent thickness will be equal to the true thickness. Yeah, you are correct. So the option will be C. Yeah. So since this is, I mean, yeah, since this section is actually vertical, that means the section itself is cross cutting the strike line 90 degrees, and it is being exposed on that vertical surface. So is it is essentially a profile section, and for this profile section, the apparent thickness that is exposed on that vertical wall, that means this surface, will be eventually equal to the uh, true thickness of the limestone bed itself. So if this is mm, the limestone bed and this is exposed, yeah, so the correct answer will be option C and not option uh, A. So option A will be, okay, option A would have been correct if this apparent thickness was given on a horizontal plane, but the apparent thickness itself is been given on a vertical plane, and since this vertical plane is perpendicular to the strike, therefore option C will be correct, not option A. So we can write this as the apparent thickness will be equal to the true thickness for a profile section, and the apparent thickness will be greater than true thickness for horizontal sections. Yes, yes, please go ahead. Mm-hmm. Mm-hmm. So you are considering this as the apparent thickness, not not this one. Yes, yes. Yeah, then we can also consider this in this way as well. So if we consider AD as the apparent thickness, so let us just refresh the calculation again. So we can say that, say for example, this is a vertical quarry, and this is the limestone bed that is going, and this is the deep, and this is the exposed vertical section. Now we can consider this as since this is, if you consider this as the strike line, then this vertical section is perpendicular to the strike line. And say for example, this is the exposure that we are considering. Now from a horizontal point of view, this would have been the apparent width of the exposure on the horizontal surface. Now this is actually the true thickness of the limestone bed. Now if we consider a line AD as the apparent thickness given, which is 18 meters, then we need to calculate the true thickness AC in this fashion. Now this angle is 90 degree minus 40 degrees, and this angle will be 50 degrees, angle ADC. And using angle ADC, we can then calculate AC as sine 50 degrees, 50 degree multiplied by AD, and this would give us a value of, so if we calculate sine 50 degrees, it is 0.766 times 18, so which is approximately equal to 13.8 meters. So in this case, considering that AD is the apparent thickness given in the question, as we have already discussed, option B will be the correct answer, not option C. This, and therefore this is the thickness of the true thickness of the bed. So we will erase this one. And we will write again like, okay, so AD is the apparent thickness, AC is the true thickness, and angle ADC is equal to 90 degree minus the deep amount, which is 50 degrees. And then we have the calculation. So we have a reminder that this is the vertical section perpendicular to the strike line. Okay, so for the next question which we were discussing, for a pure deep slip fault, there will be no strike slip component. And therefore, in this case, or in this kind of scenario, the lineations are called down deep lineations. That means the lineations will be parallel to the, I mean, the lineations, the plunge of the lineation, the plunging direction or the trend of the lineation will be parallel to the deep direction of the fault itself. Will be parallel to the deep direction. So if we have a fault plane like this, and if this is the strike line, then the lineations will go like this. So if we even then measure the rake or the pitch, will be 90 degrees because the lineations are perpendicular to the strike line. So option D will be the correct answer. That means the lineation is perpendicular to the strike line. So the pitch is 90 degrees. Okay, so the next question is, On a lower hemisphere equal area stereolate, two great circles intersect. The point of intersection represents pole to plane 1, pole to plane 2, line of intersection of two planes, and the fold axis. So of course, when two great circles intersect, so the intersection of two planes produce a line. So in the same plane, same interpretation goes to the equal. I mean, lower hemisphere equal area stereonet projection. This will be obviously the line of intersection of the two planes. So option C is the correct answer. Okay, moving on to question number 11. A dike dipping 70 degrees has a true thickness of 8 meters. Its apparent thickness measured on a horizontal surface equals to 2.7, 7.5, 8.5, and 23.4 meters. So, as we have already discussed, we are talking about the apparent thickness on a horizontal surface. So that means if this is the um, so if this is a dike, so this angle of inclination or this deep angle is 70 degrees. And the information is given is that true thickness, that means this line, this is 8 meters. So what will be the thickness of this line? So again, if we draw a triangle ABC, what we actually have to measure is the length of AB, which is AC divided by sine 70 degrees. So this is 8 meters, and then we simply divide the value with sine of 70 degree, that is 0.9396, and the value is close to 8.5 meters. So we can say the apparent thickness its strike coincides with the north-south line. It is done primarily to determine strike, dip direction, true dip, or the pole. So of course, when we rotate the the marked strike line to get it coincide with the north-south line, so we count the dip angle from the great circle by counting the great circles either from the east or the west. So therefore, this rotation is entirely done to determine the true dip angle, and therefore the option C is the correct answer. Okay, so we just have 8 more questions left. Now, a bedding plane strikes 045 degrees and dips 50 degrees southeast. Its dip direction is, so as we know, if we just follow the right hand rule, we need to add 90 degrees clockwise to the given strike direction. So the dip direction will be strike, I mean consider strike, I mean it's the azimuth of the strike plus 90 degrees. So the dip direction here is 135 degrees. So option B is the correct option. Okay, so moving on to question number 14. A lineation trains 090 and plunges 40 degrees. Which statement is the correct option? Option A, it is horizontal. Of course not, because it has the plunge value, so of course it is not horizontal. It lies on a horizontal plane. Option C, it cannot lie on a plane dipping less than 40 degrees. And option D, it must lie on a vertical plane. So a lineation lying on a vertical plane would obviously have a plunge amount of 90 degrees, so that is not the correct option. And since it is lying on a plane that has a plunge amount of 40 degrees, that also tells us that the plane is not horizontal. The line itself is not horizontal and it is not lying on a horizontal plane. Then of course the correct answer is option C, and more so because true dip is of course greater than plunge or the apparent dip. So in that rule, option C is the correct answer. Okay. So now coming to the question number 15, which is saying that which attitude is correctly expressed according to the right hand rule? 120 degree, 40 degree southeast? No, because if a plane has a strike of 120, of course the dip direction will be 120 plus 90. That means it will be in the southwest regime, southwest direction, not southeast. 30, for 30 and 40 degrees. Of course, a plane which has a strike line of 30 degree can dip 40 degree towards northeast. So option, or northeast or east rather, yeah. So option B is the correct answer, of course. But then if we just cross check if other options are also correct or not, so we will see that north 60 degree east and 40 degree southeast. So north 60 degree east means we have to get the strike line. Mm, obviously, this is this obviously is a correct answer. But then the right hand rule automatically considers that whatever the strike is, we just add 90 degree towards to it to get the dip direction. So mentioning the dip direction is not necessary when we are using the right hand rule. So in that sense, the correct answer is option B, because it actually describes what a right hand rule says in terms of describing the attitude of different geological structures. So option B is the correct answer. Okay. So question number 16 says that An anticline possesses an axial plane dipping 80 degrees. The fold is classified as, of course, since the axial plane is not 0 degrees, therefore it is not recumbent and it is not therefore neutral, then the fold is obviously an upright fold. So option A is the correct answer. Now moving on to question number 17. A lineation pitches 90 degrees on a bedding plane. It plunges, its plunge is option A, always equal to dip, always 0, always 90 degree, and cannot be determined. So as I said that pitch is equal to 90 degree means trend of line is equal to the dip direction. So the plunge along dip direction is equal to the true dip amount. So in this sense, option A is the correct answer. Okay. So for a line lying on a plane, plunge is 30 degrees and dip is 45 degrees. Determine the pitch on that plane. So what we can write is that actually tan P is equal to tan delta and sine delta, right? So we have to get this value. So tan of 30 degrees is equal to tan of 45 degrees times sine of delta, right? Therefore delta is equal to sine inverse tan 30, because tan 45 is equal to 1. So tan 30 is 0.577. So by calculating the value 0.577, we get an angle of 35 degrees. So let us consider this as 35 degrees, right? So now we can use this formula. Cos R is equal to cos plunge times cos delta. We can calculate cos 30 times cos 30 So the value is equal to approximately equal to 45 degrees. So the correct answer is option C. Okay, so let us move on to this question. The apparent dip measured along a bearing 45 degree away from strike is 20 degrees. The true dip is closest to option A 24, option B 28, option C 35, and option D 45. So the structural bearing delta is 45 degrees. The plunge or the apparent dip is 20 degrees. We need to calculate the true dip. So true dip, this will be tan inverse 10 20 degrees divided by sine 45 degrees. So this will be tan inverse of 0.5147, and the value is 27.23 degrees. So which is basically closest to option B 28 degrees. So the true dip is 28 degrees. Right? Okay. So let us move on to the last question. A sandstone bed strikes 060 and dips 35 degrees southeast. The true thickness is 15 meters. A rod cuts the bed along the azimuth 120 at 120 degrees. So the width of the outcrop measured along the road is closest to 19 meters, 24 meters, 30 meters, and 42 meters. So first we need to calculate the apparent dip along 120 degrees, right? So the structural bearing will be 120 minus 60, that means 60 degrees, right? The true dip is 35 degrees, right? And yeah, so we can calculate the apparent dip. P is equal to tan inverse tan 35 degrees times sine 60 degrees, right? And that would be 0.606. So tan inverse 0.606, and that is equivalent to, let's say, 30 degrees. Actually 30 degrees, I mean 31 degrees, and we can consider it as 30 degrees. So considering 30 degrees will make the calculations easier. Now if the true thickness is 15 meters, then the apparent thickness will be, say, D will be equal to 15 meters divided by sine of 30 degrees, and this will be approximately equal to 30 meters. So the apparent thickness will be closest to 30 meters, and therefore option C will be the correct answer. So with this, I end today's live interactive session. So we already solved 20 numerical problems related to the measurement of structural attributes, and I will see you on the next week with the new topic, which is on the concept of strain that is being measured in structural geology. Thank you.